Good evening, everybody, and welcome to what is the final evening talk of the Keele Physics Centre talk series for 2022. For those that have been with us for the last year or so, you'll know the protocols this evening, but for those that have joined us for the first time, let me very quickly just run through how tonight's proceedings will run. So very shortly, I'll introduce you to our speaker, Tommy Isaaac. But as you can probably see that we don't have attendees having their cameras on. So if you would like to ask a question at any point, please use the Q&A function, which is down the bottom of your Zoom screen this evening. And please do send them in. Tommy has expressed he's very keen to answer some questions this evening. So let's see if we can give him plenty of those to answer towards the end of this evening's talk. Tommy's talk is slightly different tonight. It's going to last about 30 or 40 minutes. Typically, the talks might be 50 minutes to an hour. So we will take a short break, a short interlude after Tommy's presentation. You can then use that to fill your glasses, go to the toilet, etc. And then we'll come back after around 5 minutes or so and then start the question and answer session. Now, as I said, this is the final talk in this particular programme, but Mike and myself, who run this particular physics centre, will be giving you information about the 2022-23 programme over the summer. And I'll pop in the chat box and shortly the mailing list. If you don't already receive our communications, you can sign up there and receive all the information about the upcoming talks. So with no further ado, I'm going to introduce you to tonight's speaker, and that is Tommy Isaaac. And Tommy is an award-winning dual-chartered chemical and mechanical engineer, focusing on supporting the decarbonisation of the UK's energy systems. His primary focus is the project management of HyDeploy, the UK's first hydrogen deployment project designed to launch the hydrogen for decarbonisation market in the UK. And I've got a keen interest working at Keele, who are a keen partner within that particular project. Alongside this, Tommy provides strategic consultancy and technical due diligence to operational asset owners. He has a proven track record of managing complex projects to overcome technical, commercial and regulatory barriers within emerging technology markets. He is also a member of various hydrogen-related parliamentary and government advisory groups, and committee member with the BSI, iGEM and IChemE. He's a recipient of the IChemE 2019 Young Industrialist of the Year Award and a published author in both industry technical magazines and peer-reviewed journals. So with no further ado, Tommy, I'm going to hand over to you. Welcome to the Keele Physics Centre, and I look forward to what you've got to offer this evening. Thank you.
Thank you, Scott. And yes, I would just reiterate that I think normally the most benefit people get from these talks is often in the Q&A. So I will be giving a kind of sufficient overview of the project to sort of whet everyone's appetite, and then hopefully we can go where all the questions take us, because they're normally the most interesting part of the presentation. That is not the right one. Okay, my apologies, it took slightly longer than would be ideal. Okay, I'm going to take it that people can all see that, and that's okay. Scott, please sort of chime in and shout if not.
It is working perfectly, Tommy. Thank you.
Lovely. So, what I'm looking to go over today is, first of all, to just cover off the regulatory landscape that we currently sit in with regard to the current gas system and the introduction of hydrogen to that system, because that really sets the overarching sort of context for the HyDeploy program. Then I'll go into an overview of the operational trials that we've undertaken as part of the program, and then I'll lay out some of the key bodies of evidence that we've developed ultimately to support the introduction of hydrogen into the system, and then we'll go into the Q&A after that. So first of all, what is the project there to try to achieve? What we're trying to achieve is to demonstrate that a hydrogen blend up to 20% can be introduced into the gas grid, and that it is safe to both transport and to use that hydrogen blend. And if we can make this case at a very broad level, then it will provide the safety assurance that's needed by the HSE to then enable hydrogen blending to take place on a widespread basis. The project itself consists of 6 partners. We have Cadent and Northern Gas Networks, who are our GDN sponsors, ourselves, Progessive Energy, who do the overall project management, the Health and Safety Science Division, who lead most of our technical work, Keele University, who were the hosts for the first trial, and then ITM Power, who provided the electrolyzer for the first trial. So the first question is, why do we bother doing this in the first place? So what's the point of blending hydrogen into the system? So at the moment, we have no hydrogen at all, really. The only hydrogen market that exists is that which exists within chemical processing. So principally, this is for the production of fertilizers, as well as the desulfurization of fuels within refineries. So it's within a sort of chemical context that hydrogen has any relevance. No one uses hydrogen to any great extent for power, for transport, or for heat. Now, the reason why this dynamic has occurred is because the system today just can't cater for the introduction of hydrogen to any great extent, because it requires too many people to move at once. So if we take where we are today, where we have no hydrogen at all being used in, say, a domestic setting, what you would need to go to full hydrogen is the co-deployment of hydrogen production and hydrogen appliances, both at the same time, to effectively complete the supply chain from production all the way through to usage. Now, that's just too much counterfactual risk all over the place to enable that to actually work, because effectively there are a load of investors that sit on the production side, and there are a lot of investors that sit on the appliances side, and both of them stare at each other waiting for the first one to move, to be able to form the business case for them to move. And because everyone stares at each other, no one moves first, and then so nothing ever happens. And that's effectively been the story of hydrogen to date. So hydrogen was cited back in the 70s as being a potential fuel of the future, but it hasn't really happened because of that commercial dynamic. If we contrast that to, say, wind, so offshore wind is undeniably the most successful low carbon technology that the UK has deployed. And the reason why that could get off the ground is because there was already a wide and very liquid demand market for electricity. So we weren't having to build electricity demand to be able to then build wind turbines to then satisfy that demand. There was already a very large demand for electricity, and so the wind could naturally come into that market and start to supplement the supply. And what hydrogen blending does is basically take that model and apply it to hydrogen. So the strategic intent of blending hydrogen into the system is to enable the existing asset base of appliances to be used, so that we're not having to change over all of the appliances at the same time that you're building hydrogen production. And that's kind of fundamentally why hydrogen blending is important. It itself does produce some fairly meaningful environmental benefits. So if we were to blend hydrogen across the gas grid, then we would expect carbon emissions savings equivalent to around 2.5 million cars off the road. But that isn't the sort of primary intent. The primary intent is really commercial, in trying to unlock that chicken and egg and start the conversion journey of hydrogen. So where are we today? We have a set of regulations that define what gas can be transported through the network that then is delivered to all of our appliances, and that's the gas safety management regulations. Now, the quality of gas that can be shifted through our network is set out in Schedule 3 of those regulations, and within Schedule 3 there is a defined limit of hydrogen of 0.1%. So there is an effective ban on hydrogen, which means that this is the principal regulatory barrier that has to be overcome to enable the hydrogen market to actually take place. and that is the purpose of the HyDeploy program. Our objective is to move that to 20%, which is what we think is the upper limit of what the current system can take before you would need to start changing out appliances. So where does the government sit in all of this? The government is relatively supportive of hydrogen, particularly Boris. He sort of, often flags it as being one of the key priorities, particularly within the energy space. And there are two documents that are of most relevance. First, it's the 10-point plan, and then more specifically, the UK hydrogen strategy. In the 10-point plan, the government have pulled out two policy impacts that they wish to enact as it relates to hydrogen. The first is on the demand side. Is on the supply side, which is to enable 5 gigawatts of hydrogen production by 2030. And then the second objective is on the demand side, which is to enable the blending of hydrogen. So they quote here as 7% by energy. That's the equivalent of 20% by volume. And they've set out a target milestone to achieve blending by 2023. Now, the UK hydrogen strategy then puts a bit more colour as to how we go from the state that we are now of no hydrogen to a state where we can enable blending. And the government's set out two prerequisites to enable what they've dubbed a policy decision, which is effectively BEIS, so the Department of Business, Energy and Industrial Strategy, supporting the regulatory process for changing the regulations. And those two prerequisites are two independent assessments. The first is a value for money case, which the government are undertaking themselves, and that's to effectively answer the question, is this a sensible thing to do? And then the second is a safety case assessment, which is being done by the HSE, which is asking the question, is this a safe thing to do? And if both of those assessments both come out with a positive result, then the government will support the necessary regulatory process that's needed to update the regulations. And they're looking to make that final policy decision at the end of 2023. So in sort of parliamentary terms, it is pretty much just around the corner. So this is just a pretty simplified graphic to show what process we're in, where you have these two independent reviews going on, first the safety, then the economic, and then those two both flow into a government policy decision. And this is where HyDeploy sits in that chain. We are developing all of the safety evidence that's needed for the policy decision, and then we'll engage with the HC throughout the year to then review all that evidence to hopefully be able to demonstrate the case that blending hydrogen is a safe thing to do. So now that I've sort of set the context of hydrogen blending, I'll then go into a bit more detail around the project itself. So I'll first talk about the trials that we've undertaken, and then I'll go into a bit more detail around the evidence that supported those trials, and it will ultimately support the case that we made to the HC. This is a £23 million programme summarised into one slide, so you can appreciate there is a level of artistic license here. But our programme is broadly split into three phases. The Keele trial, which I will speak about, and which is completed. Then there is the Winlaton trial, which we are currently in, which we're due to complete in the summer. And then the third phase, which is what we are primarily focused on now, which is filling the rest of the evidence gaps to enable that broader assessment of evidence to take place. So the Keele trial that we undertook was at Keele University between October of 2019 and March of 2021. This was the first use of gas containing any hydrogen since we completed our conversion from Towns gas, which was in 1976. So it was a relatively sort of historical moment because this was the first in the kind of modern incarnation of the gas network that any hydrogen had really entered the system. The Keele trial was using the private gas network at Keele University. That was one of the main reasons why we chose it, because Keele University looks a bit like a mini town, where the university owns the gas network. They are also the sole supplier of gas to all of the residents. So what it meant is that we weren't dealing with the myriad of suppliers that you could be dealing with. We were effectively dealing with one entity who both owned the network, transported the gas, and then sold it to the consumers, which is a pretty unique situation, because typically in the UK they are segregated between the suppliers and the transporters for obvious reasons. The trial itself was very successful, so in the sense that nothing went wrong, which is always a good start. So we built a 0.5 megawatt electrolyzer that was fed off of the university's green electricity supply. That produced hydrogen that was then stored in a 5 cubic meter buffer tank at 20 bar, and then that was injected into the natural gas supply. So in all of the images that you can see there, the bottom image is the inside of what we dubbed the credential unit, and this is effectively a fancy mixing station where we redirect the natural gas supply, inject hydrogen into it. It goes through some static mixers, and then we check the gas quality to make sure that it's all within spec and all within regulations, and then it shoots off down to all of the users. And if for any reason it strays outside those limits, it gets isolated and the supply would switch back to natural gas. That's if you have any sort of operational upset that needs to be managed. Over the course of the trial, we delivered just over 42,000 cubic meters of hydrogen, and that abated just over 27 tons of CO2. So you can sort of make that sound like a really big number, but actually it's not a huge number. The reason why it's not huge is because the trial itself isn't huge. It's only 100 homes and 30 university buildings. But the purpose wasn't to save the world. It was to demonstrate that you can transport a blend of hydrogen and natural gas, and you can use it in real world operations and real world appliances, and you won't see any issues. And that's exactly what we saw. So we didn't see any increase in the failure rate of appliances or in the leaks from the network or any call outs. Basically everything operated as it would have under natural gas, and there was no sort of operational issues that arose from the operation. So that's what we're primarily trying to demonstrate, is that systems that are built for natural gas are perfectly capable of operating on a blend, and within the bounds of the trial that we undertook, that was sort of overwhelmingly demonstrated. There is a report on this which goes into much more detail. It's a sort of 80-odd page report that is publicly available. And so if you really want to go into lots of the detail of the trial, then I would recommend you find the report. It is on the website. So where are we now? We are currently operating the second trial, which is in Winlaton. So this is in the northeast, just outside Newcastle. This is 668 homes, a school, a church, and then a few other small corner shops. And this really does look like a very small town. So we basically isolated a small village, and that village is being supplied with the blend. Now, the sort of two key differences that Winlaton has relative to Keele. The first one is that this is a public gas network, so this looks very much like the sort of physical makeup that most of the supplies of gas to our homes look like. So we're no longer on a private gas network. We are now sort of out in the wild, as it were. And from a supply perspective, this is an open market. So we have to deal with all of the suppliers of energy. So we have to have a billing regime that can cater for anyone being with any supplier and switching at any point, which is a more complex situation to deal with than just dealing with one entity. There's also a much broader range of appliances within the Winlaton trial, which is more representative of the UK baseline, and there is a greater degree of variability in the state of those appliances, from safe to not so much. That trial started in August of last year, on the 4th of August to be precise, and so far there have been no issues that we have been able to attribute to the blend in the same way that we can with the Keele trial. So both across the gas network itself, but also the downstream appliances, there have been no changes in the rates of failure of that system. So it is confirming the same findings that we found at Keele, but at a different site with more diversity and more representation of the wider UK gas network, particularly for domestics. So the trials is what everyone sort of likes to talk about and likes to point to because they're the big shiny pieces of metal. But actually, the enduring value of the programme will be the evidence base that unlocks those trials. Because although I've been using the term trial throughout this talk, trial is actually a slightly misleading term, because a trial would imply that there is a material degree of unknown that you are then discovering through whatever you're doing. And that's not really how these things work, because to enable the trials to take place, the HSE has to provide a bespoke exemption to the gas safety management regulations to enable that to happen. To enable the exemption to be achieved, you have to put forward an evidence base that demonstrates that what you're trying to do is as safe as the current system. And so that requires you to understand all of the risks, understand what will happen, and be able to demonstrate to the HSE that basically everything's in control. So they're not really trials, they're more demonstrations, because they're demonstrating that what you thought was going to happen does happen, as opposed to opening a box and trying to figure out what's inside it. So it's the evidence that supports the exemptions that lead to the trials that actually is the enduring value, because that's the stuff that will be applicable to a much broader region to enable or to unlock much wider blending. That's why I've pulled a few slides out just to go over some sort of highlights of the evidence base, and hopefully we'll then get lots of questions from that. I'm very happy to go into any element of it that people may find interesting. So firstly, the one that people are typically most interested in is what happens with appliances. The evidence that we pull together is based on assessing the diversity of appliances that are seen across the nation. If we look at natural gas appliances, the first tier of appliances came in 1976, which were actually converted Towns gas appliances. That's when all the natural gas standards formally started. We've assessed the design standards and regulations from now going all the way back to 1976, and we developed a sample of 13 appliances that was representative of the diversity of design that you could see across that population. And therefore, our kind of hypothesis was that if we can demonstrate that those 13 appliances all operate safely with a blend and perform well, then our conclusion is that the wider population of all appliances that you may see should be able to perform properly. So that was the philosophy that we undertook, and we undertook a myriad of testing in terms of traditional type testing of appliances, looking at efficiencies and combustion temperatures and all that good stuff, through to failure testing. So we effectively filled the appliances full of gas and blew them up, and had a look at how much damage occurred, and that sort of developed the evidence base across the diversity of design. Then the second axis, which is important to understand, is the baseline integrity of the appliance. So not all appliances are born equal, or at least operate equally. A newly installed appliance will operate in a very safe manner. So all of the risk comes from basically poorly performing, poorly maintained appliances. That's sort of fundamentally how people die from the use of their appliances, is because their appliance isn't working properly and it's producing huge amounts of carbon monoxide through a failed flue, which is then going into a room and leading to toxic concentrations of CO building up. So the principal sort of cause of harm is that pathway. So we had to understand how a blend may impact that pathway to be able to make an assessment of domestic safety. So what we did was take two sort of older appliances, but still relatively modern, and these had adjustable valves, so you can adjust the air-fuel ratio with a screw. And we set up the boilers to working properly with natural gas, and then we just starved the combustion of oxygen. And what this enabled us to do is simulate all of the faults that could occur within that. The sort of root cause of issues could be, say, a bird's nest on the flue. It could be lint in the air intake. It could be some kind of mechanical failure within the gas valve. We came to the conclusion that it actually didn't matter what the particular issue was that led to harm. The sort of fundamental cause of the harm was the fact that that mechanical fault was leading to a reduction in aeration of the combustion, i.e. whatever fault was happening, it was leading to less oxygen being delivered than was desirable, leading to incomplete combustion. So we simulated effectively all faults by just mechanically adjusting the air. We got flame out. So we sort of mapped the full spectrum of aeration. The graph on the left is the summary of this testing, where we did aim test with natural gas and with a blend, and you can see on the x-axis is the amount of carbon monoxide that was produced for a given aeration position with methane. And then on the y-axis is the reduction in carbon monoxide production that we saw at the same aeration with a blend. So as you can see, with the two boilers that we tested, we were getting between 70 and 90% reduction in carbon monoxide as a consequence of blending. And this is all the way up to 40,000 ppm CO, which will kill a healthy adult in around 2 minutes. So these are incredibly toxic environments. Risk benefit, because around 80% of the risk that domestic consumers will see from their use of gas is due to incomplete combustion. About 20% of your risk is due to a leak on the pipework. So the introduction of blending hydrogen almost entirely eliminates the carbon monoxide risk that results from natural gas. So it is a pretty meaningful effect that we were sort of relatively pleased to discover. Next on the list is always materials, because this is always quite sort of interesting to learn about. So clearly, materials are ubiquitous in terms of the stuff that builds all of the pipework, all of the components, all of the appliances, etc. There has to be a material of some sort that leads to the structure. We assessed all of the common materials that are used across this system, so steels, irons, aluminiums, elastomers, brass, etc., and built a representative sample set of materials. We then soaked those materials in the chamber that you can see at the top, where we did comparative soaking at high pressure with natural gas and with hydrogen. We then mechanically tested all of those coupons, or those material samples, to test for their mechanical properties. So then we had a direct comparison of the impact upon mechanical integrity as a consequence of being exposed to natural gas and being exposed to the hydrogen blend. And although there is a huge amount of evidence sort of behind all of this, the summary is that we found no meaningful change in the mechanical properties of the samples tested as a consequence of introducing the blend. So there was no statistical difference in the distributions of mechanical properties that we found across all of the materials, and that allowed us to justify the conclusion that the materials used on the network are suitable for or are as suitable to transport and be exposed to a blend as they are to natural gas, and therefore the frequency of failure of those materials should be the same, because their mechanical properties are being degraded by the construction of the blend. So what that means in terms of a risk assessment is that the frequency of events that arise from the failure of materials, which principally are leaks, remains the same. So then your risk assessment or your comparative risk assessment boils down to the consequences as opposed to the frequency of the event. And then lastly, which is probably of most interest to this audience, are gas characteristics. So we have undertaken a body of work to try to understand the kind of basic physics of the gas characteristics. The reason why we've had to commission all this work is because quite often gas characteristic analysis, particularly explosion analysis, is done at very extreme conditions. So you're looking at sort of 300 bar hydrogen whizzing down a tube at 400 degrees and then being ignited, and the results that you get from those sorts of experiments simply map down to the level that we're talking about. There isn't a lot of crossover, and there's a very small amount of evidence that is directly applicable to the kinds of scenarios that harm in domestic settings and sort of like commercial settings. Three experiments here, which forms two kind of flagship experiments that we did. The first was to try to understand leakage characteristics, where we had a box inside a box. So we were able to simulate so the internal box was our room, and that sat within a wind tunnel, and the wind tunnel allowed us to then manipulate and control the external wind conditions to then have sort of full control over the experiment. And we ran a pipe through the first box and then started to leak gas through it. We did 60 experiments in total, varying the wind condition, varying the leak aperture, and varying the leak pressure across both natural gas and blends. And then we built a CFD model of the box, which is the central image, to then validate our CFD model against the experimental results to get a reasonable a kind of reasonable interpretation of reality. Then the last stage was to make a 2D model, which we then validated against the CFD model, and then the 2D model allowed us to run Monte Carlo analysis on it, overlaying the distributions of room sizes, gas pressure, etc., etc., etc. There are lots of different factors that are at play when it comes to leakage dynamics, and they all have their own distribution. So to understand the sort of full extent of that space, you can't do it all through CFD because it would just take a millennia. So you have to be able to have a simplified model that you can run Monte Carlo analysis on to then sort of explore the sort of whole solution space. So this sort of methodology allowed us to go from physical experiment to then validated CFD model, validated simplified model, and then Monte Carlo analysis to then allow us to draw conclusions based on sort of real world inputs. The overall conclusion of the work was that you don't see any change in gas concentration as a consequence of introducing the blends. That was the kind of overall conclusion of the work. And the reason why that occurs is because if you have a large leak, so a turbine leak, you are a density-driven flow dynamic, or you're in the density-driven flow regime. So you will see an increase in leakage for the same supply pressure. But what happens when you have a leak inside a room or a box is that gas rises to the top, it finds a vent and it escapes. And it's that escaping of the gas that creates a draw into the room, and that draws air into the room over time you establish an equilibrium. And the question is, once I've established that equilibrium and I have my gas clouds sitting at the top of the room and all the pressures balanced, do I have a flammable environment within that gas cloud? And the increase in buoyancy that leads to the increase in leakage rate also leads to an increase in ventilation rate, because the ventilation is a buoyancy-driven phenomena. And what we find is that those two things basically cancel each other out. So even though you might see slightly higher leakage rates, that will induce a ventilation and create an unchanging gas cloud. And this is all, you know, well documented, and all of the experiments showed this result. And then the next one was the more exciting one, which was the explosion work. This is where we took an old storage container and then repurposed it to run explosions. So we rigged it up with lots of pressure sensors and lots of gas concentration sensors, so we could have a controlled environment in terms of the gas concentration. We used the leakage analysis from the previous work to inform the experimental conditions for the explosion modeling. So there was internal consistency with all of the methodologies. And then we effectively filled the box full of gas, ignited it, and measured the pressure waves that resulted, and then changed things like the vent areas, the amount of congestion in the room, to try and put in some real world variables. What we found is that you see an increase in the overpressure as a consequence of introducing a blend, which is not a surprise to anyone if anyone's done any explosion analysis, because it basically boils down to the which for a blend of 20%, you would expect an increase of 20%, so basically by chance, of the increase in the laminar flame speed. But quite interestingly, what we found is that you didn't really see an increase in the impulse. So the difference between impulse and overpressure is that the impulse is overpressure times time. So impulse is what a building will experience if a pressure wave. So it is the pressure wave hitting the structure multiplied by how long that pressure wave is sustaining the pressure, and it is impulse that leads to building collapse as opposed to pressure. So you can hit the building very hard with a pressure wave for a very short amount of time, and it can withstand it because it effectively doesn't have time to respond. But if you hold that pressure wave on the building, then you have time to yield it, and that's what causes collapse. We took the more conservative assessment and said we will base our risk assessment on the just more conservative assessment, and that's in line with typical explosion risk assessments, because it's the more conservative basis to take. So where are we now? We believe that the evidence that's been gathered that's justified the trials to date, that have all gone into an overarching QRA to be able to have a numerical comparative risk assessment of natural gas versus blend. We think that evidence is sufficiently universal that we'd be confident arguing the case that for all domestic installations and low pressure systems, that a blend is actually a bit safer than natural gas. Where we have gaps in our evidence base is basically as a consequence of the trial structures. So what we haven't undertaken is the experimentation on high pressure systems and on industrial users and large commercial. This is because they haven't been part of our trials to date, so there's been no driver to do so, because as part of the trials it hasn't been necessary. But clearly, as our gaze opens up and we are looking to make a much wider case to the HSE to enable blending across the gas system, we have to make the same case for industrial and large commercial as well as high pressure systems. So they are the sort of two core focuses or foci that we have of the main. That's the end of my presentation. That was informative. Hopefully it was interesting. So I think Scott wishes to take a break for a few minutes, so I'll allow him to come back in and compare.
Thank you, Tommy. That was excellent. And just for those that are wondering, we did switch your video off a few times, Tommy, just to preserve the sound quality for no other reason, so don't panic. Thank you very much for a really interesting talk, Tommy. I've certainly got a few questions that I will pose to you after our short break. But for those that are used to our normal format, we're just going to take a 5-minute break now. It's now 7:42 on my clock, so we will reconvene at 7:47. I notice we've already got a couple of questions in the Q&A, but I'm sure that Tommy's talk may have triggered a few. In fact, there we go. We've got a third question live. There you go, popping in. So if you do, if you've already filled your glasses or you don't need the loo and you have got a burning question, please do pop that in the Q&A. I will pose those to Tommy in 4 and a bit minutes time. So thank you, everybody. We'll see you shortly. Welcome back, everybody, and thank you to everyone who's posted questions. Tommy, you may live to regret asking for lots of questions. I think I can safely say we have hit an astonishing number. We're now up to about 20 questions. So to those that have posted them, I will do my very best to ask all of them. But given that we are only due to be here till 8:15, I may have to abbreviate some of them. So I will do my best to pose them to you, Tommy. It may be that you might have to turn your camera off at various points, Tommy, or we will, just to preserve the sound quality, but Sharon and I will keep an eye on that. So okay. To the very first question, and thank you, Douglas. You were the first at 7:15 to ask this question. So Douglas poses the question: I recall the change from coal gas to natural gas many years ago. All domestic appliances had to be fitted with new jets almost overnight. That program seemed to go very smoothly. Is it not worth considering a similar change to introduce hydrogen into the grid?
I think in reality it will look quite similar to that. So if we look at the appliances developed to date, so under the HyDeploy program, they've developed hydrogen-ready appliances. So that this is both boilers, cookers, and fires. At the moment, they've yet to find an appliance that can't be built. The philosophy of hydrogen ready is that you build a hydrogen appliance and then you back engineer it to gas, and it minimizes the conversion requirements once you've sold it as a natural gas appliance and gas supply changes to hydrogen. The 3 components that have been identified as being effectively the conversion kit are the 4 boilers at least, the burner, the gas throttle, and the control unit of the PCB. So these are all sort of relatively low cost and pretty sort of standard things that get changed out, particularly the burner. So I thought that at the point where we are looking to convert to pure hydrogen on a sort of individual sort of consumer level, it will look relatively similar to when converted from town's gas to natural gas.
Thank you, Tommy. Brilliant. So I'm just going to move straight on to a question from John. And he asks, one of the problems that was supposed to have occurred, bear with me, so it's supposed to have occurred when town gas was changed to natural gas, was the failure of some of the pipe sealing compounds. Obviously, you talked about some of the failure rates with some of the equipment. Have you tested the sealing compounds?
Yes. The joints, which is within the sort of gas, it's sort of old cast iron pipe with lead yarn, which is basically what leads, which is historically what's been the most leaky element of the system. Lead yarn is a pretty is a sort of well, it's a kind of artifact of history now. We use much more advanced sealing compounds, but they all fundamentally boil down to elastomers. So it's some sort of polymer which fills the space and allows an element of movement. But the basic physics is elastomer, or the basic chemistry is elastomer chemistry. So we have tested elastomers, and they're chemically inert from there is no impact.
Thank you, Tommy. Brilliant. Moving swiftly on, Rick's asked an interesting question. I'm not sure whether you'll have this information or data to hand, but he says, I believe that the ignition energy of hydrogen in air is less than 20 microjoules. What is the ignition energy of the 20% hydrogen in natural gas?
believe the calculated would be 64. So it was a calculated figure as opposed to an experimentally derived figure. But the sort of broader question that he's asking is it more easy to ignite? And from a theoretical perspective, yes, it is. In a practical perspective, it isn't really. So the harm is caused that the ignition sources of flammable clouds that lead to harm are split between two principal sources. It's electrical components like light switches and motors, and then human ignition sources like sparks from your jumpers or lighting a cigarette or those kind of things. And all of those ignition sources can be measured in the joules. So you are sort of all magnitude above what would ignite hydrogen, natural gas, or any blend of the two. So theoretically, the ignition sensitivity, but in all practical senses, it doesn't really make any difference to gas.
Thank you, Tommy. Brilliant. So Mick asks a slightly broader question, which is, what are other countries doing with regards to hydrogen, and how does your approach differ from that?
So I think this is an area where I think the UK can legitimately say that they're ahead of most other regions. I know we always say that about everything, but to the country, but the evidence would probably support that when it comes to hydrogen. Mainly because all programs at this stage are publicly funded, because there isn't a commercial case to do so. And all of the EU stuff, although it typically happens at a larger scale, it's slightly more funding structure, so is a bit slower. The UK is sort of undeniably leading the field on hydrogen. So we, for example, get contacted on a very regular occasion from overseas organisations who want to learn from the experience of the UK to then apply that same methodology.
Thank you, Tommy. Yeah, it's always really interesting. A lot of people claim that the UK is at the forefront, but I think on this particular occasion, I think you're absolutely right. We have got about 15 questions left, so I might just ask you, Tommy, to keep them as brief as possible. If people, the answers that is, if people are more interested, I'm sure we can maybe set up a follow-up, or we could share some details about how they might get in touch with you. So John asks, if there is a major leak in the open air that catches fire, is the blended mixture easier or more difficult to put out? I believe the standard extinguishing method is to fire several dry powder extinguishers into the base of the flame. So is it more difficult or less difficult to put out a blended flame?
So we haven't done comparative testing of ignition of sort of extinguishing processes for me to say here's the evidence, but I can't think why it would be any more difficult, because fundamentally you're trying to starve the flame of oxygen, and so I can't see why those methods wouldn't work with a blend. You see the same degree of thermal radiation from blended fires as you do from natural gas fires, so the extent of them is the same. So the proximity that you can get to the fire to enable to put it out is the same, and it's still visible. So I can't think why any existing methods wouldn't work.
Makes total sense. Thank you, Tommy. To T Martin has messaged, do I understand that town gas had a significant concentration of hydrogen? Maybe a quick one to answer there. Yes,
up to 50%.
Fabulous. We like those quick ones. Hope that answers, well, it did answer your question. Brilliant there. So Nithin has sent a message in. And the question is, when you examined the mechanical properties of the materials, did you examine stagnation time of the gas? I'm thinking of a scenario of appliances in holiday homes, for example, where the frequency of use is limited and it creates a density distribution in which you have more concentrated hydrogen gas.
I think you'd have. I think I probably wouldn't agree with the question. I think you would have distribution. The gas composition is sort of universal across the roads. Whether you've got active appliances at the end or not, what you wouldn't see is a kind of build up of the hydrogen. So it might be the scenario they're thinking of is effectively you've got no flow out of the system, and the hydrogen is just sort of building up within the gas network. But you wouldn't see that because effectively what you're doing there is sort of demixing the hydrogen, and the sort of natural driving force of entropy just wouldn't really allow that to happen.
Brilliant, thank you, Tommy. Yeah, I think that makes perfect sense. I know, back to Mick. Mick asks a quick question, which is there any prospect to increase the mix above the ratio that you have looked at to date?
Not within our program, but that's not to say that people don't want to look at it in the future.
Thank you, Tommy. And then Will, and thank you, Will. So Will's one of probably our youngest audience members, but always sends a question in. So thank you, Will, age 14. And it's similar to a question that you've actually in the chat box, which is what changes would have to be made to appliances, if any, in order to safely use higher proportions of hydrogen? And that links nicely to the last question about whether we might go above 20%. So what would need to happen in our homes to allow that to happen should someone else look to do that?
We probably need a smarter control scheme. So the issue isn't particularly the introduction of hydrogen, it's when it goes away. So if you set up an appliance to work on a gas that needs less air to combust, so let's just say it's 40% hydrogen and then the rest of natural gas, and then the next day the hydrogen goes away, and your appliance doesn't then know that and then increase the air, then you could slip into incomplete combustion. So you would need a sort of smarter control scheme basically to be able to control the aeration rate, which isn't how domestic appliances work today. They have a sort of tolerance range that they work in that the blend doesn't impact. But if you went to any higher concentrations, then you would start to sort of go outside that range and then potentially have combustion.
Brilliant. And then a nice follow-up to this, particularly in the current climate, Tommy. Mick asks, at the current mix or current blend, what is the expectation of cost to the consumer? So would that increase or decrease the cost at the output end?
It's a good question. So like any economic analysis, you sort of have to take it all with a bit of a pinch of salt. But based on the analysis we're going to take, looking at the supply programs that BEIS are looking to fund. So this is principally looking at hydrogen production with CCS, and the levelized cost of production that would if you were to use that hydrogen source, which is undeniably going to be the bulk hydrogen for at least the next decade, at a 20% consistent blend, you would be looking at something like £2.50 a month on the retail price of gas. Now, whether that's paid for directly through gas bills or whether it's paid for through general taxation is a political question. So whether you actually see increases in gas bills is, it sort of comes down to the politics, but in sort of raw economics, that's the kind of order of magnitude that you'd be looking at.
Thank you, Tommy. I think that's really interesting, just to put that cost context across some of the science and engineering that you've mentioned this evening. We've had two people mention the same phenomena, so I'm going to ask the question for the pair of them, which includes Simon, and they ask, I don't know the particular details, but I believe the oil and gas industry has previously had issues with a phenomena called hydrogen embrittlement. Has this been assessed in your project?
Yes, this is the main mechanism that we need to assess, which it basically needs to answer the question, are you going to have materials that fail at a higher frequency because of embrittlement? So embrittlement typically occurs with cast irons. What happens is hydrogen disassociates at the surface, and then you get hydrogen ions that migrate into the lattice of the material. It combines with carbon within the iron, and then that effectively forms methane within the lattice, and then applies an internal pressure that then eventually cracks it. That's the process. What you need is very high concentrations of hydrogen, and you also need stressors. So hydrogen really likes stress in components, because you get if you can get a nice stress gradient, then it has a higher association with ionic flow. Cycling valves, for example, are a good example of that. At the pressures that we're talking about here, and the partial pressure, particularly of hydrogen, you just simply don't see it at those levels. So it's a potential concern at much higher concentrations, but not at the blend levels that we're talking about. It's worth sort of noting that in the oil and gas sector, they're very different operating conditions. You'd be looking at far greater temperatures, far higher pressures, much more onerous operating conditions relative to the gas network today. So it's a phenomenon that has to be assessed, but experience with the oil and gas sector and the gas networks.
That's really interesting. Thank you, Tommy. And that leads us really nicely on to the next question from Peter. And again, it's a materials-based question. And he asks, in terms of the modelling that you mentioned, that you were using 100% hydrogen rather than a blend. Why was this, is the first part of the question. And the second follow-up is there any potential impact on the materials from natural gas with higher blends, e.g. increased sulfuric acid formation with the increased hydrogen levels?
So the reason why we use pure hydrogen is because what matters is the partial pressure of the hydrogen. So it's just experimentally simpler to use pure hydrogen at different pressures than a blender at say 5 times the pressure. It also allows us to be quite conservative, because we can just use we can use sort of 8 bar hydrogen or pure hydrogen, and that would simulate around 40 bar blend. So that was the reason why we chose to use pure hydrogen. Sorry, I've forgotten the second part of the question. Be able to repeat it?
Yeah, of course, Tommy. Bear with me. So the second part of the question was, is there any potential impact on the materials from natural gas with higher blends, for example, an increase in sulfuric acid production based on the higher hydrogen levels?
I don't think so. So sulfuric acid isn't a sort of typical thing that you would see in a gas network. You more likely in sulfide as your kind of sulfur-containing element, along with the odorant. But hydrogen sulfide primarily comes from the gas well, as opposed to being produced within the gas network.
Brilliant, thank you, Tommy. I'm going to stick to combine 2 questions together now. So thank you to Penny and to those that asked a similar question in the chat box itself. And the question is, can this work read across to the possibility of 100% H2 in the gas grid? And if not, what is needed to make 100% gas grid possible? And I attached the question also to a comment in the chat box from Simon, who was it Simon? Yeah, who said basically that how much of the town gas network is therefore left when you get to around 20% blend? So can we get up to 100% in the gas grid? If so, what do we need to do? And how much at 20% is left of the actual infrastructure from a town gas network?
So gas, but in terms of the read across between 20% blend and the sort of conclusions are clearly not really transferable, because the basis of the assessment is different, but the methodologies are relatively generic. So the way the way in which design the risk assessment, the experimental methodologies that have developed the evidence to go into that risk assessment are kind of universal, or they are dependent on the question that's being asked. So you could ask a different question and use the same processes, and then you ask that question. But in terms of the sort of actual data, I wouldn't say there's a huge amount of read across, because there's such a difference in the gas quality. I think the second part was around sort of reuse of the existing assets. So we're the whole sort of blending is to reuse the existing system and to justify that that's a safe and appropriate thing. Kind of accepted that downstream of the meter, i.e. appliances, will need to change. That's accepted. The major question, if you like, is what do we do with the gas network? Is our gas network to transport hydrogen? I think that's basically the critical question that has to get answered. And if the answer is that the future of hydrogen looks relatively bleak, if the answer is yes, then I would say it looks relatively buoyant. So far, coming out of the development would imply that it's the latter, but the evidence is the nor HC. So we have to still, we can't claim victory yet.
Thank you, Tommy. Right, so we've got, I think, 8 questions left in about 8 minutes. So I'm going to ask you to try and keep them as short as possible so that hopefully we can get through all the questions that have been posed, Tommy. And that starts with a follow-up from Will, and hopefully this is a nice quick one. Regarding the trial at Keele, and obviously the suggestion that that's now been finished, and obviously you've now done a trial on a town, what are the next steps in terms of scalability for your project?
So the next steps in terms of scalability is basically full deployment. We've sort of reached the limit of what you can sensibly do with the trial, because the way the gas system is designed is that you have 4 pressure tiers, and you can think that 3 nested networks, with a sort of headline network. They run at different pressure tiers. All domestic are on the 4th tier, that low pressure tier. At the medium pressure, so 1 tier above that. If you were to then say, I want to run a trial at the next pressure tier, which is the intermediate pressure or pressure tier, the kind of breadth of your trial at that point is so broad, so many sub networks beneath that, that you're effectively doing look very similar to rollout. You're sort of no longer in a trial scenario, you're basically in mass rollout. So we've done what you can sensibly do with trial, and bridging any evidence gaps with lab data and with desktop studies, and then to HC and government to be able to justify mass rollout.
Thank you, Tommy. That's really interesting, because that brings us on to a quick question from Mick, and he says, do you have any sense of how long it would take to convert the whole of the UK network to this particular blend? And is there any logic to only converting some parts of the network?
So there's no sort of conversion, so to speak, with a blend. It's really a function of HC blend, which is entirely a function of the supply. So if we can make it, you'll get a blend is the answer. So it comes down to when can we build sufficient capacity to be able to provide everyone with a blend. That's probably still some years away. 1 gigawatt target by 2025, 5 gigawatts by 2030. But our usage of gas underpins our entire economy and all of our energy system. We up to 1,000 terawatt hours of natural gas, which is just a vast number. So being able to provide even 7% with hydrogen is going to take at least a decade to be able to build out that capacity. We're talking energy generation something like an order of magnitude more than wind. It's vast numbers.
That actually is really interesting and leads us into a lovely follow-up question from Peter, and he's posted a question which is: hydrogen production at scale and a lack of storage and distribution networks has for years been a key issue to using it more widely as a fuel, for example in fuel cells in vehicles. Doesn't this usage therefore just further undermine any strategic shift to fuel cells?
I would argue no. because I don't really see them as being competitive. So the problem with saying is that you're back into my argument of chicken and egg, that you don't have to be fueled with just waiting for the pipe to be there. Again, you've got a set of investors on one side and there's a set of investors on the other. So how do you create the system that enables there to be a hydrogen pipe there that can then be fueled from? And it's not going to be through fuel cells, because it would have happened. If that was the case, it needs to be based on a first step which uses an existing demand to enable the supply to be developed, and then more kind of bespoke applications, if you like, so ones that we don't currently use can then springboard off of that supply to then be used. So I don't really see a supply, because if there is a commercial model that promotes supply, there really is a limit to capacity, because it's fundamentally based on natural gas supplies, which are for all intents and purposes unlimited. The current to the market notwithstanding. So I don't see there as being any real competition between two. I think blending is the thing that rises boats, basically.
Thank you, Tommy. And I notice we've only got 2 minutes left, so I'm going to try to combine some of these last few questions. The first one is a very quick one, hopefully, regarding the fact that hydrogen is such a small molecule and therefore much easier than methane to potentially leak. How do you identify these potentially minute holes in the distribution network?
It just that process doesn't really happen. So you don't get leak sizes of hydrogen that couldn't allow methane through. So the atomic radius of hydrogen is around 80%. That is smaller.
Sorry, Tommy, I think you just broke up towards the end there, but I think we got the gist of the answer. And on that note, I think what we're going to do is we're just going to finish off with a final question from Rick, because I noticed we are very close to our end time. And I think it's a nice segue potentially into a future talk, perhaps from someone that might be able to talk a bit about this. But Rick asks, is it the intention to use the 20% blend in the UK power stations operating gas turbines driving electrical generation? So is that a potential for this particular area of research? And of course, it could be at this point that we've lost Tommy, but bless him, he was in a hotel room and I think the Wi-Fi did get progressively worse. So unfortunately, Rick, I'm not sure. Oh, Tommy has reappeared. So Tommy, I don't know if you heard the question. But essentially, so I'll very quickly repeat it. Rick asked, is there any intention to use the 20% hydrogen blend in some of the UK gas turbine power stations?
If they're connected to the distribution system, yes.
Oh, fabulous. Okay, brilliant. On that note, ladies and gents, we are now at 8:15. And I think we've answered the vast majority of the questions. Some of them, and I apologise, John, I can see you've just posted one. I'm afraid I think we're out of time. However, it's clear that we do have a real interest in this. So there is potential perhaps for a future talk, and maybe bring Tommy back or someone else from Progessive Energy. Yeah. Yes, over to you, Tommy.
I'm happy to stay on for another 5 minutes. So if there are questions, it's up to everyone else, really. I'm quite happy to stay on.
Oh, fabulous. Okay, in that case, if anybody does want to hang around, we've got 2 more questions, so I think it's only fair then if you're happy, Tommy. So the first one was from John, and he asked, why was such a low limit on hydrogen set by the gas regulations? Someone must have had a reason for setting it quite so low.
Yes, they did. It was regulatory expedience. So when the regulations were first being developed, they were being they were developed as a consequence of the privatisation of the gas markets. So it was basically when British Gas stopped becoming a nationalised entity that owned the gas system, and then we had a private system. And the government asked HSE, how do we do this safely, and thus was born GSMR. At that point, our entire gas supply was natural gas from the North Sea. So when we're putting together a gas quality standard, it makes sense at that point to effectively align the gas quality stipulations to whatever's coming out of the well on the North Sea, because it's easier to manage. And if you look at gas quality graphs, what matters is the WOBE number, which is a bulk gas characteristic composition, the P and N number, which is the amount of nitrogen and propane and the hydrogen content. They're the kind of three critical gas characteristic parameters that you need to understand to people interpret. Given there was no hydrogen coming out of the gas well in the North Sea, it was decided that percent, and the three-dimensional graph, two-dimensional graph, and it becomes easier to manage. That's the reason for the 0.1 limit. It's simply easier to manage.
Thank you, Tommy. And actually, there's a really nice way we can combine these final three questions into one. They all essentially, so thank you, John. Thank you to the anonymous attendee. I'm not sure who you are, and to Will again. I'm going to combine your questions into one, which is essentially around the green credentials of this hydrogen, Tommy. So, for example, at present, John says there is not enough wind generation to provide green hydrogen, and about 40% of our electricity comes from burning gas. And obviously you mentioned electrolysis being the source of the hydrogen in this particular project. So in future, you know, what is the current source? Obviously electrolysis, but is there a way in which we could generate green hydrogen to be injected into this particular supply?
So technically, yes, but I suppose like anything, once it comes in, sort of once you try to deploy it on scale, it comes down to the economics, and economically, it's just not really possible to do. So, you know, sort of gas bills are very topical at the moment. The sort of two broad category, or the two ways that you can make hydrogen at the moment are electrolytic or reformation with CCS. Everyone likes the green stuff because it's, you know, it's sort of nice and cheap, which is very expensive. You know, you're talking something like £160 a megawatt hour for produced, something like £45 a megawatt hour for the reformation with natural gas CCS. That means a natural gas price of around 20 to 25 a megawatt hour. The green credentials of green, assuming it's a green, it is a fully renewable source, if you like. The blue hydrogen, as you're looking at thermal efficiencies of around 55% of the production process, and you're looking at capture rates of kind of 98, 99%. So there are a level of residual emissions that do go up the stack on the order of 2%. Is an issue that would need to be dealt with at some point, but you are talking about a carbon reduction saving on the order of 98% on a kind of per energy basis for a price that's far more competitive than green hydrogen. So although I think the end everyone would like to aspire to is a fully green hydrogen system, we have to recognise that we live in an economic world, and achieving sort of, you know, 95 plus of the answer at a quarter of the price is probably a sensible thing to do.
I really, really appreciate that. Thank you, Tommy. I think to finish on a, as you say, an economic question, particularly in the current context, is a very apt place to finish. By far and away, that is the most number of questions we've ever posed to a speaker. So thank you, Tommy, for not only answering such a broad range of questions from chemistry through to mechanical engineering through to the physics, but but also putting up with the hotel Wi-Fi, which is never easy. So I just wanted to say, on behalf of the IOP Keele Physics Centre, thank you very much, Tommy, for this evening. Thank you to still the 30+ people in the room that were obviously interested in all the questions. They've been fabulous, so thank you for that. I will very quickly post in the chat the link to our mailing list. So for those that are still here, if you're not on the mailing list and you want to find out more about our future lectures and talks, please do sign up and you'll be the first to hear about it. So thank you once again, Tommy. It's been a real pleasure to host you this evening. Thank you to everybody for taking part. I really do hope you have a wonderful summer, and all being well, we should be back with our first talk in October. So with no further ado, have a good evening, everybody, and we'll see you again soon. Bye for now.
Bye-bye.